Hey everyone, I want to continue our study of irreducibility, and we're going to remain in the classical case. So we're studying irreducibility over Q. And remember, last time we had this important result, right? This was 23.9. 23.9. So it was something like this for polynomial f of x in z bracket x. If f of x is reducible over Q, then f of x is reducible over z. Right, so you can factor an integer polynomial over the rationals. Then by doing a little bit of sliding of constants, you can actually factor it over z. And so the first thing I want to do, there's a consequence of this. So let's put it here. So this is corollary 23.10. And so what I want to do is take a polynomial. So let's let f of x equal to a0 plus a1x plus dot 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 plus a sub n minus 1 x to the n minus 1 plus xn. So I want it to be a monic polynomial, meaning that it has 1 as its leading coefficient, the coefficient on x to n. And this is going to be a polynomial with coefficients in z. Now if, and I want to make sure that this, I got to say one more thing, with a0 not equal to 0, right? So that's got to be a non-zero leading or a constant coefficient. Now, if f of x has a 0 in Q, then there exists an integer, say little b, such that f of b equals 0 and a0 is divisible by b. So and b divides a0. And you know what? This should kind of remind you of the rational root test. In a way, this you could think of as it's an analog. It's the integer root test. Right? So if with a polynomial that is monic and has a non-zero constant coefficient, if you know that it has a rational root, then it actually has an integer root, and that integer root has to divide the constant coefficient. All right, so that's a nice little test. So for the proof, let's see. So let's take our rational root. So let's let, say, alpha in Q be such that f of alpha equals 0. Now remember, we had this thing called the factor theorem that tells us that if we have a root, right, then we can factor it in a certain way, right? So then there exists say little g of x in Q bracket x such that f of x equals x minus alpha times g of x. Okay? So that's by the factor theorem. In fact, let me just say that. So that's due to the factor theorem. Okay, fine. Now what have we done? We have an integer polynomial that we factored over Q according to our previous theorem. We know that we can factor it over Z. So by theorem 23.9, there exist little a and b in Z, and a, let's say, g hat of x in Z bracket x, such that f of x factors as, so we've got a degree 1 polynomial over q that's going to be replaced by a degree 1 polynomial over z, and so that would look like an ax plus b, and then it'll be times a g hat of x. All right, so that's what our previous theorem told us, that we can factor, if we can factor over q, then we can factor over z, and this is what it would look like. Now let me think here. Oh, okay. Now, I don't know what this polynomial g hat of x looks like, but think about whatever it is, right? It's got some coefficients. When you multiply the leading coefficients, right, we have to get x to the n. So we have ax times whatever the leading coefficient over there is. That has to give us 1, which means that a equals 1. So since the leading coefficient of f of x is 1, we see that e has to equal 1. Also, when we multiply things out, the constant coefficient is going to be b0 times the constant coefficient here. So also, the constant coefficients satisfy. So what we would have is a0 is equal to b times, I don't know, c, where c is the constant coefficient of g hat of x, and so b divides a0. All right, so it's not a particularly difficult result. The proof is actually kind of nice. And here's the point, or how did this happen, right? It relied on two things. First of all, the factor theorem, right, which got us to this step. Then theorem 23.9, which gets us to this step right here. And then it's just arithmetic. It's just sort of looking at how coefficients have to multiply out. Now, one thing to point out. All right, we use theorem 23.9 to prove this, call it the integer root test. But typically, so we'll say it like this, though, theorem 23.9 is often applied in contrapositive form, which means this: if f of x in Z bracket x is irreducible over Z, then f of x is irreducible over Q. And so I want to sort of show how this goes with an example. And so the example I want to look at, what I'd like to do is, so let's prove that the polynomial f of x equal to x to the fourth minus 10x squared minus 19 is irreducible over Q. So what we have here, we've got a polynomial with integer coefficients. And so according to what we just set up here, this observation, it suffices to show that it's irreducible over Z. If we have that, then we can conclude that it's irreducible over Q. So for our proof, right, it suffices to show that that f of x is irreducible over Z. Okay, so now there's two possibilities. Let's think about it. We've got a degree 4 polynomial. And so how would such a polynomial factor? If it was going to factor, it would either be degree 1 times degree 3, or it would be a product of two degree 2 polynomials. And so we're going to consider each of those cases separately. So let's look at case 1. If f of x has a linear factor, say x minus a in Z bracket x, then what do we know? Well, what would we have to know then? Well, then we would have to know that our root, it divides negative 19, right? So then a would have to equal plus or minus 1 or plus or minus 19. And if you check, I mean, you just go back and plug that in, right? If you plug plus or minus 1 in here, you definitely don't get 0. Same thing if you plug plus or minus 19. So you can just check that f of plus or minus 1 is not equal to 0, and f of plus or minus 19 not equal to 0 either. Okay, so that takes care of the first case, right? There is no degree 1 factor, which means that it has to factor. If it's going to factor, it's got to be degree 2 times degree 2. So case 2, yeah, so what would that look like? So suppose suppose that f of x is equal to, so let's see, it would be, I'm going to write it as x squared plus ax plus b times x squared plus cx plus d. Notice, because f of x is monic, right? It has a 1 for the leading coefficient. That means that both leading coefficients of the factorization have to be 1 also. Right? Oh, so here for some A, B, C, and D in Z. So now I'm going to multiply this mess out, and let's see what happens. So if I multiply, we have x to the 4th plus, let's see, the x cubed terms are going to be a c and an a, right? You know what, instead of trying to get fancy, I'm just going to multiply it out, and I'll take the time to do this. Okay, so when I get x to the 4th plus cx cubed plus dx squared plus ax cubed plus acx squared plus adx plus bx squared plus bcx plus bd. Collect all the terms, so this will be an x to the 4th plus a plus c x cubed plus, for the x squared terms, d plus ac plus b, that's x squared, plus for the x terms, looks like an AD and a BC. And then finally, plus BD. And this has to equal our original polynomial, which is x to the fourth minus 10x squared minus 19. Right, so we have to show that this can't happen, and that if we can get there, then we can conclude that our polynomial is irreducible over Q. Okay, so what do we get? So this gives us, well, it tells us that A plus C has to equal 0. Which other one's drawing a random wall down? Yeah, AD plus BC, that's the degree 1 term, also has to equal 0. D plus AC plus B has to equal, oh, of course I erased my polynomial, but it's 19, right? Oh, there it is. Oh no, the middle one, that's got to equal minus 10. And then BD has to equal minus 19. All right, so it gives us 4 equations that we can work with. So let's see. For the first one, I'm gonna solve here. Let's say substitute. I'm gonna say substitute C equals minus A. And so now what we'll get is AD minus, which one do I want here? BA equals 0. So I'm substituting into this one right here, and then if I factor, that's going to give me an A times D minus B has to equal 0. So A equals 0, or oh yeah, let's do the other substitutions too. So this would be D plus B minus A squared equals minus 10, and BD equals minus 19. Okay, so that reduces it to these 3 equations right there. And then I think I just want to consider 2 cases. So if A equals 0, from this equation right here, that's one of our possibilities, then we have D plus B equals minus 10. So B equals minus D minus 10. And then if I substitute into this equation right here, so minus D minus 10 times D equals minus 19. Oh, right, which I can then, I'm going to turn this into a quadratic equation. So this is negative D squared minus 10D plus 19 equals 0. And you can just use the quadratic equation to show, sorry, minus 10D squared here. So now use quadratic. Right, D has to be an integer, and you can just use the quadratic formula right here to show that there's no integer solution. So use quadratic to show no integer solution. Okay, so that rules out that a equals 0. The other possibility is that b equals d. So if b equals d, then what we have right down here, b squared equals 19. That's clearly impossible. Minus 19, which is impossible. So what do we have? Let me just kind of, let me finish off this example with the conclusion, right? So since the polynomial x to the fourth minus, was it minus 10x squared? Where'd it go? I lost my polynomial. Yeah, minus 10x squared minus 19 has no linear or quadratic factor in z bracket x, we conclude that it is irreducible over Q. So that argument is a little, ad hoc-y, I guess. So, I mean, the polynomial is kind of rigged to make things not work out. But remember, trying to show that a polynomial is irreducible can be a very difficult process. And so this is one of the things that you have to go through, right? Is try to sort of make a combination of various tests that we have, plus some arithmetic, to rule out all possible factors. And, I mean, you can see that is kind of ad hoc-y. So what I'd like to do, or what we're going to do now, is develop another test. And so let me just remind you, so recall the homomorphism, which we called phi, from z bracket x to zp bracket x, from lemma 23, I think it's 23.7, yeah, where we reduce the coefficients mod p and we're going to use this notation. So we use the notation phi of f of x equals f bar of x, right? So remember, that bar notation means that we've reduced each of the coefficients. And so in this next theorem, we're going to use that notation. So theorem 23.11, this is called the mod p test. And so it goes like this. So let's let f of x be a polynomial with coefficients in the integers. It needs to be non-constant, so it's got to be degree 1 or greater, and let p be prime. If f bar of x is irreducible over zp and the degree of f bar of x is equal to the degree of f of x, then f of x is irreducible over Q. Now, what you want to do is recognize the significance of this. Typically, right, if you have when you're working with polynomials over an infinite ring, right? Z is infinite. There's an infinite number of possible ways that you could potentially factor, right? Because there's an infinite number of coefficients. However, if you're working over a finite, right, when the ring, or in this case the field of coefficients is finite, that means that there's only a finite number of possible ways to factor a particular polynomial. So this replaces an infinite situation, an infinite question, right? Does this polynomial, can we factor this polynomial? Using a couple, well, here over Q, but using polynomials from Z, it replaces it with the question, can we factor a related polynomial, the one where we reduce the coefficients mod P over ZP? Replaces an infinite question with a finite question. So this is a very, very useful result. Okay, so now for the proof. So let's see, what do we need to do? Well, let's assume that the hypotheses hold. We're going to go for a contradiction, right? So suppose, let me set the stage here. So suppose f bar of x is irreducible over zp bracket x, that the degree of f bar of x matches the degree of f of x, and that f of x is reducible over Q. Now remember our theorem 23.9 tells us then if it's reducible over Q, then it's actually reducible over Z. So by theorem, by 23.9, there exist, say, g of x and h of x in z bracket x, such that f of x equals g of x, h of x, and this is an honest factorization, which means that the degrees of both g and h are strictly less than the degree of f. So and the degree of both g of x and degree of h of x strictly less than the degree of f of x. Okay, so now what do we have? So now we have, so let's see, we've got f hat of x is equal to phi of f of x, which is equal to phi of g of x times h of x, which is equal to, because we've got a homomorphism, this is phi of g of x times phi of h of x. And what's this? This is, of course, g bar of x times h bar of x. Now, okay, so let's see. What does this tell us? Well, it certainly looks like it's telling us that f of x is reducible. Although we need to check, right? We need to make sure that the degrees of these polynomials are actually strictly less than the degree of f bar, right? So since the degree of g bar of x, well, that's less than or equal to the degree of g of x, which is strictly less than the degree of f of x, right? When you reduce a polynomial mod p, it's possible to kill off the leading coefficient. So when you apply phi, right, the degree of g bar could be less than the degree of g of x. So that's why I've got this less than or equal to right there. So this is less than or equal to degree of f of x, which is equal to the degree of f bar of x. And same thing with the h's. So and degree of h bar of x is less than or equal to the degree of h of x, which is strictly less than the degree of f of x, which is equal to the degree of f bar of x. Now we can say, this tells us that f of x, or f bar of x, so we can say it follows, so since, I guess I'm in the middle of a paragraph or a sentence here, it follows that f bar of x is reducible over ZP. That's a contradiction. All right, so that completes the proof. Well, let's see. I probably should do one example, Okay, so let's do an example of applying this. I don't want to burn you out by going too long, but let's do one example. So let's show that the polynomial f of x equal to x to the fourth minus 10x squared minus 19 is irreducible over Q. Does this example look familiar? Yeah, we did this using sort of an ad hoc method before. Now what I want to do is use the mod p test. So, well, okay, so how do you do the mod p test? Well, what you want to do, start off with mod 2, see if it works. If that doesn't work, try mod 3. At some point, right, the number of polynomials gets larger and larger as you increase the size of the coefficient field, so you don't want to get too large, right? But mod 2 and mod 3 are actually reasonable to work with. So we first try mod 2. Okay, so what does that mean? Well, let's see. F bar is going to be x to the fourth plus 1. And f bar of 1 is 1 plus 1, which equals 0, which means that this polynomial is reducible over Z2. All right? That tells us the test fails. Right, so our goal is to find a p for which f bar, right, when we reduce mod p, for which it's irreducible. If it's irreducible, then we get to conclude that our original polynomial is irreducible. Okay, so now we're going to try mod 3. So first, okay, so f bar of x, that'll be an x to the fourth, mod 3, so that's a -1. I'll write it, yeah. -1, which is +2, so plus 2x squared. And then if I reduce 19, mod 3 is also -1, so that'll be a +2. All right. Now you can just run through the elements. So let's just say note that f bar of x does not have a 0 in Z3. And so what does that mean? It means that f bar cannot factor as a degree 1 times a degree 3. And so f bar does not have a degree 1, so a linear factor. That does not mean that we're done, right? This is a degree 4 polynomial, so it could have a degree, what am I trying to say? It could have a degree 2 factor. Okay, so we now show that f bar of x does not have a quadratic factor. So yeah, okay. So we want to simplify things a little bit, or simplify the question. So let's say it like this. So first, note that if f bar of x has a factor of the form 2x squared plus say ax plus b, then by multiplying by 2 times 2x squared plus 2a plus ax plus b, right? If this is a factor, then 2 times it is also a factor. So then this is a factor, and let's write this out. So this is x squared plus 2ax plus 2b is a factor as well. If you have a factor, then a constant multiple of that factor is also a factor. And so notice then, that allows us to just work with factors that are monic, right? The quadratic factors with a degree, where the leading coefficient is a 1. So thus, we can restrict our consideration to monic quadratic factors. Okay, so now we're working over Z3, and there are exactly 9 such polynomials, and so let's actually write them out. Why is there 9? Well, because I have, where'd it go? I have 3 choices for the first entry, 3 choices for the second entry, so that gives us 9 altogether. So there are 9 such polynomials in Z3 bracket x, and let's just write them out. Okay, so there's x squared, there's x squared plus 1, x squared plus 2. Is that how I want to write them? Yep. There's x squared plus x. There's x squared plus 2x. There's x squared plus x. Whoop, plus x plus 1. There's x squared plus x plus 2. There's x squared plus 2x plus 1, and there's x squared plus 2x plus 2. Now, I'm going to draw some arrows here. So that one, and that one. Now, what I want you to do is to just observe or check, if you like. It's easy. You can quickly check that the polynomials that do not have arrows pointing at them have zeros in Z3. So let's say check that the, let's say, non-arrowed polynomials have zeros in Z3. And so what that tells us is the ones that don't have arrows pointing at them cannot be factors of this polynomial right here, because otherwise we would have a linear factor for f bar. Right? So f bar, if it's going to factor, if it's going to have a quadratic factor, then that quadratic factor will have to be one of those three right there. And you can actually verify using long division, so I'm just going to say now, so now use long division to show that f bar of x has no linear quadratic factor in Z3 bracket x. And let me just do one example. Let's say I'll show that this one right here is not a quadratic factor. X squared plus x plus 2, and I need to divide that into, what was my polynomial? X to the 4th plus 0x cubed plus 2x squared plus 0x plus 2, I think. Is that right? Let me just make sure. Yeah, mod 3, that's it. Okay, so x squared goes into x to the 4th, x squared times. So we get an x to the 4th plus x cubed plus 2x squared. Subtract, that will give us negative x cubed. Minus 1 is the same as positive 2, so this will be a 2x cubed plus 0x squared plus 0x. X squared goes into x cubed, or 2x cubed, it goes in 2x times. So this will be a 2x cubed plus 2x squared plus 4x, which is x. Subtract, this will give us negative 2, which is positive 1, plus 2x plus 2. That goes into here. X squared goes into x squared one time. And now clearly we're going to get a non-zero remainder. So what do we get? We get x. Right? And so that tells us then that this polynomial does not go cleanly into this polynomial, so it's not a factor. Okay, so what did we do? We showed that f bar is irreducible over Z3, which means that f is irreducible over Q. So let's just write that down. So since f bar of x is irreducible over Q over Z3, it follows. We conclude that f of x is irreducible over Q by the mod 3 test. So that's the idea. If you can find a prime number p such that f bar is irreducible over Zp, then you can conclude that the original polynomial is irreducible over Q. Okay, so that's a good place to stop. We will pick up with this next time.